During this video, I'll go through the process of predicting products of hydrolysis reactions. So recall that during a hydrolysis reaction, water is being added to a compound, causing the compound to split into two or more smaller compounds. This process also uses a catalyst, and so you may simply see the word catalyst, or you may see the word acid, or you may see H plus to represent acid, but a catalyst is needed to help this reaction occur at a much faster rate. But during that process, the molecule splits and it breaks into two different compounds. After it splits, the water molecule is then added between those two compounds. One gains an H, the other gains an OH. So if we go through this process, and you'll see that this process is basically the same for the different types of hydrolysis reactions that can occur. So remember, you'll see the hydrolysis of an ester. You can see this for thioesters or even amides. But the initial process is still the same. So I'm simply going to redraw this structure, making it just a little bigger. And so for this example, we're starting with an ester. And so remember, an ester, that's when you have your carbonyl with an OR group attached, so an oxygen that's also bonded to carbon. And so in order for hydrolysis to occur, the molecule has to split. The most reactive bond is going to be the bond that is the easiest to break. Which bond is more reactive? So think about these bonds that are present. You have many different carbon-carbon bonds. They're nonpolar. No change in electronegativity. You also have carbon-oxygen bonds. Oxygen and carbon bonded together creates a polar bond. So this carbon-oxygen double bond is polar, indicating that the electrons are unevenly distributed in the bond. Instead of being evenly spread out, they're attracted more to that oxygen. The same thing with this carbon-oxygen bond. It's also polar, as well as this carbon-oxygen bond. It is also polar, meaning that the electrons are being attracted towards that oxygen. So you have these three carbon-oxygen bonds, two single and one double. All of these represent polar covalent bonds. And so these bonds are going to be more reactive because the electrons are not evenly shared between these atoms, and instead the oxygen is trying to take electrons away from that carbon. So if this carbon can free itself, it doesn't have that tug of war of electrons going on with the oxygen atom. So if we look at the different bonds, so I'll simply label where these dipoles are located, A, B, and C, just so that we can distinguish and talk about the different bonds. So A represents a carbon-oxygen double bond. B and C are both carbon-oxygen single bonds. When you're comparing single bonds to double bonds are shorter, but they are also stronger. The stronger a bond is, the more energy it's going to require to break that bond. So recall, during chemical reactions, old bonds break, new bonds form. And so in a hydrolysis reaction, the old bond must break in order to split this molecule. Because the double bond is going to be stronger, it requires much more energy to be broken. The energy needed to break the double bond would have already, have broken the single bond. And so, keeping that in mind, we'll know that A is not going to be the first bond to break or the easiest bond to break. It will be B or C. Not only do we have A being stronger, we have that carbon-oxygen double bond, but we also have this carbon-oxygen single bond. So the same carbon that was bonded to the oxygen for A, so double bonded to that oxygen, is the same carbon that is single bonded in bond that is labeled B. This carbon has oxygen atoms on both sides that are trying to take those electrons. So this oxygen is being pulled in two different directions. If we look at bond C, we have an oxygen that is bonded to an oxygen. A carbon that is bonded to an oxygen. So that carbon is being pulled towards that oxygen. The electrons in that bond are being pulled towards that oxygen. So you have one atom trying to play tug of war with that carbon at bond C. However, the carbon that is bonded in A and B is being pulled in two different directions. This causes more stress on that carbon. It creates a more unbalanced field. And so as a result, that carbon is going to be more reactive. If that carbon could get rid of one of those oxygen atoms that's bonded to it, it can help to relieve some of the pull in the different directions. So it can help to relieve some of that stress or tension that is being placed on it. Again, looking at A, that double bond is going to require much more energy to be broken than B. So because this carbon is being pulled different ways, and this single bond is not going to require as much energy to be broken as that double bond, this would be the bond to break. It may sound confusing, but just think about if you are being pulled in too many directions. When you have too many different things going on, you're trying to give up something. You're going to give up the thing that is the easiest to give up. And so in this case, the easiest thing to give up is this single bond because it won't require as much energy as the double bond. And so thinking about that, now we can proceed with predicting the products of this reaction. So my recommendation when you're trying to draw the products, once you've determined which bond is broken, and you'll see that it is always the same bond. It is always the carbon of the carbonyl and that single bond to the heteroatom that is present. Remember, a heteroatom is any atom besides carbon and hydrogen. So we have the carbon of our carbonyl and we have the single bond to this heteroatom, which in this case of an ester is an oxygen. So we know that bond is broken. So to predict the products, because we know we're going to end up with multiple products, go ahead and redraw your compound, but do not show that bond that was connecting those atoms. So bond B was the bond that's broken. I'm going to redraw my compound, my ester, but I'm going to leave out that bond and show it as two separate compounds. This is how we get those two separate compounds. But recall, during hydrolysis, water must be added. We see the water above the reaction arrow. When you have things that are written above or below a reaction arrow, they are part of your reactants. So they are needed in order to start that reaction. My other recommendation, think of water as HOH. It's still H2O, but just think of how it's actually bonded. You have an oxygen that is a central atom bonded to two hydrogen atoms. When that water molecule plays a role in the hydrolysis reaction, it's going to be added to that original compound. But when it's added, one end, so one of the new compounds will gain a hydrogen, whereas the opposite end or the opposite compound would gain the OH, the hydroxyl. So by showing water as HOH, that can help you to remember that we're adding this back to these two molecules as H and as OH. So again, let's think through how we're going to finish this. So H and OH. Oxygen is the second most electronegative atom, period. That means that oxygen is able to attract electrons. If I were looking at the actual hydrogen bonded to the oxygen, which is also bonded to the hydrogen. So if I were looking at the actual structure of water, I would have this Lewis structure where I have these non-bonding electrons. I have oxygen-hydrogen bonds, which are very polar bonds. So those electrons are being attracted towards that oxygen, causing that oxygen to have a partial negative. So it's not an actual negative, but it feels as if it has that negative charge. The electrons are trying to be pulled away from the hydrogen. So they feel as if they are missing electrons. So they feel as if they have positive charges. So keeping this in mind, when we look at our HOH, we basically have the same thing. The hydrogen that is being added is missing electrons. The oxygen of the hydroxyl that will be added feels as if it has extra electrons. So think about that partial positive and that partial negative as we go to add the hydrogen or the hydroxyl to our two new components. So we have this carbon of our ester, of our original ester. We have the oxygen. So if I go back to my original structure, I had already indicated how my dipoles were drawn. So what that would tell me is that this carbon, because it feels as if it's missing electrons, would have the partial positive. The oxygen would have had the partial negative. Now remember, in chemistry, opposite charges attract, but like charges repel. So if my carbon is partial positive, it's going to want to pair with the opposite, which would be the partial negative. My oxygen, which was partial negative, will want to pair with the opposite, which is the partial positive. So look at how our charges and how our water molecule was broken up. The hydrogen represented the partial positive. So that partial positive wanted to be paired with your original partial negative, which came from your oxygen. So that tells me that my hydrogen is going to add to the end that had the oxygen. My partial negative is going to want to pair with my original partial positive, which is where my carbonyl group was located. So now you ended up with two different compounds. You have your carboxylic acid, and I'll redraw them just to show they are two different compounds. And you also have your alcohol. I can simply show them both, or I can show this plus that. It still means the same thing. So the product of this hydrolysis reaction gave me my carboxylic acid and my alcohol. Again, if we had just gone back to where we started, looking at that initial compound, we broke this bond. Each end gained either a hydrogen or a hydroxyl. Your carboxylic acid end, so whichever end had the carbonyl, this becomes your carboxylic acid, so to gain the hydroxyl. The opposite end simply gains the hydrogen. And so those are the products of this hydrolysis reaction. We can look at another. So let's say we had the hydrolysis of a thioester. A thioester is similar to an actual ester group. However, that thioester, you have a sulfur replacing an oxygen of an ester. So now you have an SR group instead of an instead of an OR group. And so we'll add our water and we'll have some catalyst. So this one I'll just show as H+, just so that you're not stuck on seeing it one way. Again, the bond that is broken is the easiest bond that will help to relieve some of the stress being added to this carbon of the carbonyl because it's being pulled two different ways. So it's always that carbon heteroatom single bond that breaks. Again, once you get this part, go ahead and redraw each piece as they initially were, but don't show them connected. Don't change the number of carbon atoms. Don't change how the atoms are arranged. Simply disconnect those pieces by breaking that bond. From there, one end gains the H, the other end gains the OH. It's always going to be your heteroatom that gains the H and your carbonyl that gains the OH. And so we can look at hydrolysis reactions of esters. We can look at them for thioesters, and we can also look at the hydrolysis of an amide. In this video, I'm going to simply leave it at the ester and the thioester. I'll do a separate video for the amide because it has an additional step that is not taken for esters and thioesters. So it starts out the same, but there's an additional step that applies to only that class of compounds. And so in this video, we'll stop here looking at the hydrolysis of an ester and a thioester. The results for both. The product will always be a carboxylic acid, but the second product will either be an alcohol or a thiol, depending on what the substrate, which is your reactant, so what substrate was undergoing hydrolysis.